So I'd like to start today with a few remarks on low-degree Hochschild cohomology and their relevance in the context of block theory. So let me just start with HH0, and of course everybody knows that if you take the HH0 of an algebra, then this is canonically isomorphic to the endomorphisms of the algebra viewed as a bimodule, and that can be identified with the center of the algebra. So this is as far as generalities go. In block theory, what matters is that this also counts the...
We can hear very well here.
It is switched on, so... Okay, is that better?
Okay, thanks.
All right. So we have this these canonical isomorphisms. So for block theory, in the situation that we've been considering all through, we have our field of fraction of a complete discrete valuation ring which maps onto its residue field of prime characteristic P. And let's for a moment assume that the characteristic of K is indeed 0, and let's take a finite group G. And let's also assume that the field K has enough roots of unity. This is a blanket assumption I always keep making. Then, well, we know that the group algebra over such a field is a direct product of matrix algebras. The matrix algebras are, matrix factors are parametrized by the irreducible characters of the group G, and they are of the form Kg, and then you multiply by the primitive idempotent in the center of Kg, so E of chi, so primitive idempotent in the center of Kg, corresponding to the irreducible character chi. Okay, so these are matrix factors. Now, if you have a block algebra of OG, and you extend the scalars, then very obviously what you're going to get is a subset of these matrix factors, because this is a direct factor of Kg. So this is the direct product of certain matrix factors, where chi runs now over a set of irreducible characters, which I denote by of B. This is a subset of the irreducible characters of the group G, uniquely determined by the block B, and that gives you actually a disjoint union of the irreducible characters of G in terms of the irreducible characters of the blocks B. Every matrix factor has a one-dimensional center, as matrix algebras do, and so the order of the set B is just the same as the O rank of the center of the algebra B, and that is also the same thing as the K dimension of the center of the algebra over the residue field little k, because centers map surjectively from OG onto little kg. And I mentioned yesterday Donovan's conjecture, which says that if you fix a defect group of a block, you should have at most finitely many Morita equivalence classes of block algebras. One of the consequences of that is that this should bound the number of ordinary irreducible characters associated with a block B in terms of the defect group. And that's indeed the case. This is one of the earliest results in this direction. This is the theorem of Brouwer and Veit, which goes back to 1959. and which says that if you have B a block with a defect group P of order, let me write this as P to the D for some positive integer D, or actually that includes D equals to 0, then the number of irreducible characters in this block is bounded by, I'm going to write down the bound they found in their theorem. There have been some improvements of this bound lately, but in later years. But the thing is that what matters really is that we have a bound which uses only the defect group. And if you look at the proof, it's a bit of magic with character theory. And the statement itself is really not a statement about characters. It looks like on the surface it is, but because the number of irreducible characters is nothing but the dimension of the center over little k. This is really just a statement about the block as a k algebra. So there should be some proof out there of this statement which should allow to prove this without using character theory, but no such proof is known currently. Merita equivalent algebras have isomorphic centers, and so Donovan's conjecture would imply that there are only finitely many commutative K algebras which arise as centers of blocks for a fixed defect group. And it's been observed by Kesar that if you throw in Brouwer Fight and the result I mentioned yesterday by Cliff, Pleskin and Weiss, then you do get that consequence. So this is an observation by Kesar, and it's really an immediate consequence of Brouwer Fight. And the result of Cliff, Pleskin and Weiss I mentioned yesterday, which said that the center of any block algebra over the residue field little k always has a basis with multiplicative constants in the prime field Fp. So this is a rationality result. Putting these things together is giving us that there are only finitely many commutative K algebras up to isomorphism arising as the center of, I should really say K, B, little k's over K of blocks B of finite groups with a fixed isomorphism class of defect groups. So with a fixed defect group P. It's a different method to actually classify those finitely many commutative algebras. So that has been done in a number of cases. So what we can classify actually the commutative algebras that arise in this way if, well, the classic cases are where the defect group P is cyclic. Then we have these various P2 groups, so Klein 4, dihedral, quaternion, and a few more. And this comes from, as an immediate consequence of Erdmann's work on classifying these blocks up to Merita equivalents. And then there is the number of other cases. Again, we can also classify those centers for elementary abelian of order 8. That already creates a lot of trouble. One actually needs the classification of finite simple groups here. And very recently there have been partial results of rank 4. So this is for blocks with one simple module. Partial results by in a paper on the archive by Landruck and Zambale. So this is very recent. So it's one thing to say that there are finitely many, it's a totally different thing to actually figure out what those finitely many are. It is, interestingly enough, an open problem what the relation is in the opposite direction. If you fix yourself a bound on the number of irreducible characters, does that give you a bound on the defect group? That is an open problem. So this is always revolving around this not very well understood relationship between the two types of invariants that count as blocks. On the one hand, those invariants that rely just on the algebra structure of the block, and then those invariants which come from the fact that these block algebras have a group in the background, and the defect group is one of those. Let's move on to HH1. So what can we say about HH1? First of all, HH1 can still also be characterized in a very elementary way. So let A be an algebra form. Second, it can be an algebra of an arbitrary commutative ring. So what's the derivation? Derivation on A is a linear map. Linear with respect to the ground ring, which satisfies the Leibniz rule, f of a b is equal to f of a b plus a times f of b. So for instance, take the derivatives on a polynomial ring is the derivation on a polynomial ring. And if you fix an element, then the map C, blank, defined by C, A equals to the additive commutator CA minus AC for all A. That's a derivation. That's a trivial verification. And these derivations are called inner derivations. So the picture we have is that in the linear endomorphism algebra with respect to the base ring, but this is an algebra, and it's also a Lie algebra with the usual bracket of endomorphisms. Well, you just send them to the commutator. Inside there, we have the set of derivations. That is a sub-Lie algebra, no longer an algebra. So if you compose two derivations, you may not end up with a derivation. But if you take the bracket of two derivations, you do get a derivation. Inside there, we have the set of inner derivations. And that is a Lie ideal in the set of derivations. So we can take the corresponding quotient, and what we get is the HH1 of A, which can be canonically identified with the quotient of the derivations on A modulo the inner derivations on A. And this is then obviously a Lie algebra because I've taken the quotient of a Lie algebra by a Lie ideal. So the multiplication in Hochschild cohomology also tells you that HH1 is a module over the center. So a module over HH0. So it's a module over the center. That's obvious. And then there's one last remark I wanted to make, which is that if K is a field of characteristic P greater than 0, then in fact HH1 is a restricted Lie algebra. Where does the P power map on this Lie algebra come from? We have the map which takes a derivation and sends it to itself composed P times. So this is P times. So what you need to check is that you start out with a derivation and you compose it P times with itself, you end up with a derivation, and that uses obviously characteristic P here. And so this is the P power map which gives you a restricted P algebra structure. There are a number of naive questions that one could ask at this stage. One of them is what Lie algebras show up as HH1 of a block, or in fact of an arbitrary finite dimensional algebra over a field. And then you can narrow that question down a little bit by asking, well, what are the simple Lie algebras that might possibly show up as HH1 of a block algebra, or for that matter, arbitrary finite dimensional algebra. And the thing is that in prime characteristic, the situation is rather more complicated than in characteristic zero. So the classification of simple modular Lie algebras is usually more difficult than the classical situation in characteristic zero. And it seems that from calculating examples, there are only very few simple Lie algebras that seem to be showing up in block theory in this way. And that would actually be interesting to nail down more precisely, because that would be yet another property that sets block algebras apart from arbitrary algebras, finite dimensional algebras. The first simple Lie algebra in prime characteristic which doesn't have a characteristic finite dimensional characteristic zero analog is the Witt algebra that was discovered by Witt in the 1930s. I think he didn't publish his results. In modern terminology, the Witt algebra, let me write it, W1, is simply the HH1 of a cyclic P group. And so a cyclic P group algebra is isomorphic to truncated polynomial algebra, where you mod out by the pth power of the variable, and then you can write down the basis of the derivations. They're not linear derivations, it's a commutative algebra. And so you just look at the derivations fi, which send the variable to the i's power, and you can do this for 0, I running from 0 to p minus 1, and then you see that this is actually a simple Lie algebra. And this Lie algebra is not the tangent space of some smooth algebraic group, so this is really different from what happens in characteristic zero. It was then Jacobson who proved a little while later that, in fact, these things work for arbitrary elementary abelian groups. I think it's published in 1943. So if P is an elementary abelian P group of rank n for some positive integer n, then, and let me just denote this as Wn, this is the first Hochschild cohomology of P, is again a simple Lie algebra. And obviously these do show up in block theory, because they show even up as the HH1 of a P group, so that certainly does show up. Can anything else show up? So the question really is, can any other simple Lie algebras in prime characteristic P show up as the H1 of some block. And I suspect no, but it's difficult to calculate examples, so I don't have enough examples to make this a conjecture, but there's a reason for thinking that there might not be any other simple E algebras showing up from block theory. So what I suspect is going to happen is that if the H1 of a block algebra is simple, then actually it is one of those, and the block is Morita equivalent to the elementary abelian P group. These are the so-called non-potent blocks with elementary abelian defects. So there's some reasons to think that this might be true, but I'm not going to make this a conjecture. There's something else one could ask at this stage, which is even far more naive than this question. That is is actually this H1 always non-zero? And so here I'm going to make a conjecture which is a bit risky, but anyway. So suppose B is a block of some finite group algebra KG with a defect group which is not trivial. Then H1 of B is non-zero. The hypothesis non-trivial defect group is necessary, because if the defect groups are trivial, then this is a matrix algebra, and then its H1 is of course zero. Now there's some interesting background to this type of question, which is that there's a paper by Fleischmann, Janishak, and Lemkin from 1993, which implies that the H1 of a group algebra is non-zero if the characteristic P of the field divides the group order. Again, that's a necessary condition. What is extraordinary about the proof is that it requires the classification of finite simple groups, and that feels really wrong. One should not need the classification of finite simple groups to prove such a statement. So this requires the classification. And if you're familiar with Hochschild homology, you can probably right away see where that comes from. That comes from the fact that Hochschild homology has additively decomposition in terms of centralizers of elements in the group. And the cohomology of one of the centralizers is non-zero precisely if its O upper P is a proper subgroup. So there you have full-blown group theory, and that is something one can check using the classification of finite simple groups, but one doesn't know how to prove this in a purely algebra theoretic way. Although there is another interesting paper around this subject, which is due to Gerstenhaber and David Green, which is from just a year later. They were aware of this work, and so they looked at some bit of deformation theory, which I'm going to mention later, where they showed that what's known as the Donald-Flanagan conjecture, if true, would imply this. The Donald-Flanagan conjecture is a conjecture about every finite group algebra in characteristic P like this to have a semi-simple deformation, and that semi-simple deformation would be what they call a jump deformation. There's a bit of deformation theory there, and that forces the H1 to be non-zero. So there is definitely some interesting, there are some interesting connections here. let me write down one result which gives you a lower bound, not just for the HH1, but in fact for the HH1 as a module over the center. And so that's what I'm going to write down is a criterion which basically is in terms of the quiver of the algebra A. One of the there are loads of calculations, loads of interesting papers that try to calculate HH1 in terms of combinatorial information using the quiver. One of the problems with that for us in block theory is that we are very rarely in a position where we actually know the quiver of a block algebra. And so we have a hard time making use of those results. But so let me write down one of those results which is typical for this kind of business. This is from a recent paper of Benson, Kisser, and myself. It's on the archive at the moment. So let's take for A a split finite dimensional symmetric K algebra. So I'm throwing in a few hypotheses which I know are satisfied for blocks. Then the number of loops in the quiver, which is just the same thing as taking the sum of the dimensions of the x1s of simple, of course, always up to isomorphism. This is bounding below the dimension, not just of HH1, but actually the dimension of HH1 as this socle over the center of HH1. So we're looking at HH1 as a module over the center, and then we look at what gets annihilated by the radical of the center. And the reason why we might be interested in this is that constructions like this have good invariance properties with respect to not just Morita equivalences, but slightly more general stable equivalences. One quick remark is that about this non-vanishing of HH1 is that if, I haven't mentioned what this is, but I'm just going to mention that if Bouet's abelian Heathcote conjecture holds, that would imply that HH1 of B is non-zero if B has a non-trivial abelian Heathcote. So there's some connections with other conjectures in this area. Okay, so I briefly hinted at a work of Gerstenhaber on deformation theory. There's one slightly more structural look at derivations, which I would like to describe briefly now. That is the concept of integrable derivations. So, integrable derivations. So that goes back to Gerstenhaber in a paper 1964 as the following. You start out with a finite dimensional K algebra, and you consider phi an automorphism of the algebra formal power series over A. Because A is finite dimensional, this is really the same thing as power series and then tensored with A over K. And so this is an algebra over this ring of power series. So we want this to be an automorphism as algebras over this ring, such that phi induces the identity on A itself via the canonical algebra homomorphism which identifies t to 0. So what does that mean? Well, this means that if you apply phi to some element of the algebra A, which is a degree 0 element of A double bracket t, then what you get is, well, you should be getting back A, and then plus all sorts of other stuff, which is divisible by t. So you get something like d1 of A times t plus d2 A times t squared, etc. And obviously, the EI are endomorphisms, linear endomorphisms of A. And by comparing the expression of phi of AB and phi of A times phi of B, one sees immediately that D1 has to be a derivation. So, comparing these expressions, phi of AB in degree 1, shows immediately a totally trivial exercise that D1 is in fact a derivation. So D1 is a derivation on A, and these are called integrable, and we're using interchangeably the same term integrable derivation also for integrable class and HH1. So we denote by HH1 int the integrable classes in HH1, and well, these are subspaces of HH1, and they have some nice invariance properties. So there's, for instance, one theorem I'd like to mention, which is by Farkas, Geis, and Markus, I believe, from 2002. Which says that basically that this space, HH1 of integrable derivation, class of integrable derivations, is invariant under Morita equivalences. And they prove all sorts of other things in that paper. But, so this is one of the things. And a remark is that if your field is actually the complex numbers, then every derivation is integrable. So every derivation is integrable. So how do you construct for a given derivation? How do you construct an automorphism? Well, we construct this simply by some exponential construction. So phi of A is equal to the sum n from 0 to infinity of d n times this composed with itself divided by n factorial and t to the n. So d to the n is just the composition of d n times with itself. And one checks that this is an automorphism and that it gives you back this derivation d as an integral derivation. One should say that in characteristic 0 these things work well because in fact HH1 in this case is just the tangent space of the algebraic group, the connected component of the outer automorphism group of A as algebraic group. And this is just not true in characteristic P. So in characteristic P things are just more complicated. So already the Witt algebra W1 has must be dn applied to A. if I'm not mistaken. Let me just yeah. Okay. And d to the 0 obviously is added. Okay, so already the Witt algebra has derivations which are non-integrable. I've been wondering while doing calculations whether the space of integrable derivations actually always is a solvable algebra. I haven't found anything to that extent to that topic in the literature, but one should certainly ask that question. So, coming from block theory, there are two things in which we would like to possibly adapt this a little bit in terms of getting to a generality that we encounter typically in block theory, which is that first of all, working with the ring of power series isn't sufficient. We would like to work with more general complete discrete valuation rings which reflect change of characteristics that we're always interested in. So this is one of the things that one element of generality we would like to introduce. The other element of generality is that we would also like to see an invariance property of the notion of integral derivations under slightly more general types of equivalences, namely stable equivalences of Morita type. So that this becomes really a notion which is invariant under the stable equivalence of Morita type. I'm going to mention those a little later. The reason for that is that in block theory we encounter all the time stable equivalences between variant block algebras, and we have a hard time to figure out what to do with those stable equivalences because we don't even know about their most basic invariants, whether they're preserved or not, such as the number of simple modulus, for instance. I'll come back to this theme. So let me start with the first of those two issues that I want to address. One is we're going to work now again with our ring, a complete discrete valuation ring. The radical is then generated by a single element. We have our residue field, which is always of characteristic B. And we would like to use that rather than double brackets T for our integral derivations. So let's take an algebra over O, which is free of finite rank over O. Group algebras, of course, have that property. And so then we have all sorts of intermediate algebra. So of course we have the algebra which is over the residue field where we just divide out by I. So this is the same thing tensoring with K over O. So I'm going to denote this sometimes as a bar. So this is now a finite dimensional K algebra. And we have these intermediate Artinian algebras, pi to the n, n is positive. So these are free over the Artinian quotients of O. And of finite range. So we're going to play with these algebras to see whether we can define a notion of integrable derivations in that, for that slightly more general setting. You should note there's a slight shift now in notation. This algebra A would correspond to what I denoted earlier, the extended algebra. Whereas this A corresponds to this A bar. I'm shifting notation a little bit to keep it as simple as possible. Because this A is now the algebra over the O. Okay. So let's define the group of automorphisms, subgroup of automorphisms, odd sub n of A. That's simply the group of automorphisms which become the identity on this Artinian quotient A mod pi to the n. A, and then the corresponding automorphism is just the image of odd n in in the outer automorphism group of the algebra A, which is the same thing as the quotient of the automorphism group by n automorphisms. And the proposition is that, well, these automorphisms can be used to construct derivations on these Artinian quotients. So we need a little more hypothesis than in the Gerstenhaber situation. I'm going to write those down. So we need to suppose, as before, we need to suppose that the canonical map from the center of A to the center of the Artinian quotient is surjective. So that's a condition which in this kind of setting is automatically satisfied. But here this may or may not be satisfied. So let's now take an automorphism in plot sub A. What does it mean? Well, that means that we have a map D on A such that if you apply alpha to A, you get back A plus pi to the n times D of A. Because by definition, alpha is the identity modulo pi to the n. So this is a linear map. And D itself need not be a derivation, but the map on this Artinian quotient, a to the pi n a, induced by D is a derivation. And the second statement is that this correspondence sending alpha to this derivation is going to be inducing a well-defined map from the outer automorphism group out n to the Hochschild cohomology HH1 of this quotient. So, second statement, the correspondence alpha to D as before induces a group homomorphism from the outer automorphism group out of n of A to HH1 of A mod pi NA. And we can even say what the kernel is. With kernel the automorphisms which are the identity mod pi to the 2n. So this amounts to checking that if alpha is an inner automorphism, then D induces an inner derivation, etc. So that everything is well defined. And we use the obvious definition, so we call a derivation on this Artinian quotient or its class in HH1 of that quotient. We call that A integrable if it is in the image of this map. The group homomorphism as in the proposition. And we denote by HH1 sub A of A mod pi to the n the set of A integrable classes then HH1. This is always a subgroup because it's the image of a group homomorphism, but one loses a little bit of the properties that one has in the Gerstenhaber setting. So for instance, this is not necessarily anymore an O submodule of HH1. It's certainly a subgroup, but also that subgroup depends on more parameters than in the Gerstenhaber setting. So for starters, you could have two different algebras A whose quotients multiplied to the n are isomorphic, and then the notions of integrable derivations will actually be different.
I have a question. Are your automorphisms of Roman A always trivial on?
Oh yes. Okay. So I'm always talking when I write down the automorphisms of an O algebra. I always mean the ones which are actually trivial on the coefficients O. If you don't make that assumption, the picture looks very different. So yes, they're all algebra automorphisms. Then I want to complete that definition here. Let me just actually do this here. So, the canonical map from A mod pi to the n A to A mod pi A, which is this A bar, induces easy a map of the first Hochschild homology groups, and we set the Hn sub n of A bar to be the image of the integrable derivations, A integrable derivations. This is slightly sloppy notation because this depends not just on n, it also depends on the lift A, and I'm going to call these n integrable. So this is again a subgroup now of the HH1 of A bar. And this HH1 sub A really depends on A itself. It also depends on the ring O. If you go over to ring extension, then actually this group will change. So the ramification of the ring O will play a role. If you are in the classic case where A is just the coefficient extension of a finite dimensional K algebra as in the Gerstenhaber setting, then you just recover the original notion of integral derivation. So there's nothing new that comes in. So, but what happens now is that we get a nice invariant statement for integrable derivations that extends a little bit the results I mentioned over there, from Morita equivalences to stable equivalences of Morita type. So let me mention what that is. This is a notion which also goes back a long way. So this is a definition which is due to Roy around 1990. So if you have two O algebras and M and AB bimodule, N a BA bimodule, both finitely generated projective as left and right modules. Then M and N are said to induce a stable equivalence of Morita type, well, if they are a Morita equivalence up to projective jump. If you tensor two of these modules together, then you get back as a bimodule, your bimodule A, but possibly plus projective jump. So plus a projective bimodule, or which is the same thing as a module over A tensor A opposite projective, and you get the same thing the other way around. This should be B plus projective B tensor B op module. So if the jump is 0, then you're in the situation of a Morita equivalence. And if the jump is non-zero, well, then you have a slightly more general type of equivalence. These will still induce stable equivalence between the module categories of A and B. And the problem with stable equivalences is that we have a patchy knowledge as to what, at best, as to what they preserve. So I'm always hunting actually for anything that could possibly be invariant under stable equivalences. The reason why we are really interested in stable equivalence of Morita type is that they are omnipresent in block theory. There are stable equivalences of Morita type between block algebras all over the place. Let me just give you a couple of examples. And so it's easy to come up with stable equivalence of Morita type in block theory, and it's then very hard to know what to do with them. So examples. Let's just consider the example at the prime 2. We have the algebra of the alternating group A5. Inside we have the algebra of the alternating group A4. What do we take for M? Well, we just take the bimodule, which is sort of the induction bimodule. We take the group algebra of A5 and restrict it on one side down to OA4, and on the left side we keep the full structure of OA5. For N, we just do the dual thing. We take OA5, but we restrict the module structure on the left side to A5. And that gives you a stable equivalence of Morita type. It's very easy to see, by the way. In this case, of course, because this is a very small example, one knows exactly what happens. The other example, well, one also knows pretty well what happens is if you have a cyclic Synow P subgroup, non-trivial, and if H is the normalizer of the unique subgroup of order P, then you have the same phenomenon. So you have the group algebra of G, inside sits the group algebra of H, and for N you take the induction bimodule OG restricted on one side to AH, and for N you do the same thing on the other side. So these are bimodules, they're both free on both sides. And again, you get a stable equivalence of Morita type. This is also a special case of something more general, which is called strongly P-embedded subgroups. So every strongly P-embedded subgroup will give rise to a stable equivalence of Morita type, but in general, we do not know how to handle these stable equivalences. In the cyclic case, obviously we do, because that is a finite representation type situation. So we know how to deal with that. So the theorem I just have time to write down is now saying that we have the invariance that we hope for, and we have it in a nice and compatible way with the automorphism groups that lie above those integrable derivations. So here's the theorem. So this is quite recent. So we have A and B O algebras, and there are a few hypotheses now that we need. We could just take the hypothesis symmetric, that we don't really need. What we need is that these algebras should be self-injective. So the quotients over little k are self-injective. And I'm going to assume that they're split self-injective. That's not necessary. One can get away with something slightly less. But for simplicity. And we again need the assumption, which we know to be satisfied in block theory, that the canonical maps from the centers over O to the centers over little k are surjective. That's the hypothesis one always needs to throw in. So I suppose further we have M and N bimodules which induce a stable equivalence of Morita type. Stable equivalence of Morita type between these two. Then not only do we have a nice isomorphism between the A-integrable derivations of any of these Artinian quotients, but actually we can always lift this equivalence to an isomorphism between the outer automorphism groups sub n of A, which induce those integrable derivations. And then you can also show, this is a bit technical, that actually this is induced by a functor which we control very well, namely somehow the conjugation which with n and n on the left, n on the right, will induce this isomorphism. That requires an interpretation of integrable derivations in terms of some Box-Stein homomorphisms that show up naturally in this context. I haven't mentioned, but I would like to mention finally, the p-restricted structure. Stable equivalences of Morita type preserve the entire positive part of Hochschild cohomology. In degree 0, things are slightly more complicated, so centers are not necessarily preserved under stable equivalence of Morita type. But in the positive part, they preserve the Hochschild cohomology, including its algebra structure, including its Lie algebra structure. That's a result by 3 authors, König, Liu, and Zhou. And, but what they leave open is whether the p-power map is preserved under stable equivalence of Morita type. And we don't have a complete answer to that, but a partial answer is given by a PhD student of mine, Leonard Rubio, recently. So if you're in the Gerstenhaber setting, if you start out with finite dimensional self-injective algebras and M and N bimodules which induce a stable equivalence, then the p-power map, p in brackets, sends n integrable derivations to n times p integral derivations, and we have a commutative diagram as one would expect it, namely, so we start out with n integrable derivations. Here, the p-power map is going to go to n integral derivations, and here we have isomorphisms with the n integral derivations over b that we know already from the previous theorem, and again this commutes with the p-power map. We do not know whether this commutation extends to the entire first Hochschild cohomology, so there's definitely some more work that needs to be done. And the technical background machinery that goes into identifying these isomorphisms comes from the general concept of Box-Stein homomorphisms associated with certain short exact sequences. And I think this is a good place to stop. Thank you. Yes, actually, yes. So I should have really written this down. When you have a derived equivalence between two self-injective algebras, that will induce, by the result of Rickard, a stable equivalence of Morita type. And then this result kicks in. So as a consequence, at least in this setting of self-injective algebras, the answer is yes. In a more general setting, I don't know.
The result that we had that it's invariant under equivalence. So I always add this divided and it's invariant on the right. So saying that for self-injective it is.
Yes, that's right.
Any other questions? If there are no further questions, let's